Now let's talk about some applications of matrices and statistics and probability. So assume that x1, x2, up to xn are random variables. Then I could stack these in a column vector, like so. Again, maybe this is maybe x1 is the age of a person chosen at random, and x2 is their height, and xn is the number of siblings that they have. Okay. So this entire thing is a random vector. It's a random vector in n-dimensional space. It's some arrow that points from the origin out into some random place in 3 space. It's a random vector. The expectation of this random random vector, and I'll put little doodads on the ends of x's there on the x there to indicate that it is in fact a random vector. This thing is just defined to be probably the way that you'd think. It's the vector of expected values. Okay, so I just take the expected values of each one of those random variables and stack them in a vector. Okay, it's the sort of the center of mass, if you will, of the random cluster, okay, the random spatial distribution there. The covariance matrix of a random vector x contains the covariances of all the pairs of the random variables that are elements of x. I could write covariance of this random vector, then I might express it, or you might see it something like this, sigma squared of x, or with the x in the subscript maybe even, but it's just defined to be the matrix of covariances. Okay, of course this first one will be just the variance of x1, and I have the covariance of x1 with x2 and so forth, all the way over to the covariance of x1 with xn. These are the random variables. Next over here you have the covariance of x2 with x1. Covariance of x2 and x1 is the same as the covariance of x1 and x2. 2 with xn. Got n of these things, so whoops, n, right? Covariance of xn with x2. Oops. The covariance of xn with itself. Remember, this is the same thing as the variance of xn. So, because let's just review a little bit here to maybe make some of this make sense. Recall that the covariance of 2 random variables, say x and y, is defined to be the expected value of x minus its mean times y minus its mean. Okay, this measures the average sort of degree of linear association between these 2 random variables x and y. And it turns out, after just a little algebra, you've seen this before for sure, this is the expected value of x times y minus the expected value of x times the expected value of y. Okay. And the covariance of of course, by the way, so the variance of x is just defined to be, can be defined to be the covariance of x with itself. Okay, you should note from this expression here that in fact the covariance is a symmetric function. It doesn't matter what order you put these 2 random variables, you get the same thing. Okay, but so that's why we have when we have the covariance matrix for random variables, we have variances all along the diagonal here and covariances in the off diagonal here. So sometimes this is called, sometimes this matrix is called the variance covariance matrix, variance covariance matrix, because it has variances in it along the main diagonal, or just called the covariance matrix, whatever. Also, you should note that because covariance is a symmetric function, this matrix is in fact symmetric. So the covariance matrices are symmetric. Symmetric. You can see that from looking at the structure of this. These elements are the same. These elements are the same. Right? These are the same. Now, so I could also then I could write the covariance of this random vector. I might be able to what if I maybe I could write this as the expected value of we'll take the random vector minus the expected value of that random vector, and then times this vector. Transpose. Okay. Now take a look at what you have here. This covariance matrix needs to be n by n, right? Okay. Now this is a column vector. This x vector is n by 1, right? It looks like this guy up here. N rows, 1 column. This will also be n by 1. This is n by 1. This is n by, n by 1. If I take the transpose of, if I subtract this from this, I get an n by 1 is sitting in here, right? If I take the transpose of all of this, so all of this is going to be 1 by n. 1 by n, right? Now, so look at what you're going to essentially be doing here. You're going to take element by element, you're going to be multiplying the values in these vectors. So look, remember this, so this, all of this is n by 1 minus an n by 1. This is a column n by 1. Once you take the transpose of this, this is a row, okay? Now what happens if you take an n by 1 and dot it with a 1 by n? You get an n by n, right? Here you're going to get this number times that one will be the element in the upper left-hand corner of the matrix. If I take this one times the next one, you get the next one. Okay, so multiplying matrices this way, two vectors this way, a column times the row, you'll get a square matrix that's n by n. Okay, and so then if I take the expected value of this matrix that you get here, it's essentially it's actually you can extend this definition. If I have a bunch of random variables in a matrix, the expected value of a random matrix is just, we'll take it to be the matrix of expected values. Now suppose that x and y are column vectors of data values, okay, and I'll write them small this time because we're thinking about data. They've got numbers in them, and we want to talk about the sample means, sample variances, and sample covariances. I can express the sample mean in terms of vectors. I know exactly what that is, right? You add up the numbers in this vector and divide by the length of the vector, right? So maybe I could say it's 1 over n times, could I say it like this? A vector of 1s, a 1 by n vector of 1s there. That's 1 row with n columns, and then times, I'm going to dot that with the vector x. Yeah, because see here, I'm just saying 1 times the first element plus 1 times the second element plus 1 times the third element and so forth. This gets me, this right here is the sum of 1 times the x values, like that. And then so I'm adding this up, adding those numbers up and dividing by n. Okay? And in a similar fashion, I could say that the sample variance is that's 1 over n minus 1 times, I have to take x minus x bar times a vector of 1s, let's see, an n by 1 vector of 1s transpose against the same thing, right? Now, I'm going to leave it to you to see this. You may need to write out the matrices and vectors, but make sure that you understand that this is in fact consistent with the formula where you know, the sample variance is right. It looks like this: xi minus x bar squared over n minus 1. Okay, so you want to check and make sure that these two actually are actually the same thing. Similarly, I could write down the sample covariance for two variables x and y. If I've got those data values there, as 1 over n minus 1 as x minus x bar times dotted with these 1s. It's a n by 1 transpose, but then put y's in here, right? Just put dots in there for dot product, okay? And times 1, like so. Furthermore, let's suppose that x n by m is a matrix of data values, and each column contains observations on a different variable. Then the sample covariance matrix, you know, you might indicate it like this or something. Okay. S for sample would be 1 over n minus 1 times, I'm going to take my matrix of data values, I'm going to subtract. I need to somehow subtract the mean of the x values for each column. I need to subtract off a column of the means for each column, right? So it's so you could say j times an n by m times multiplied by the data matrix x, right? And transpose, and then times the same thing, but without the transpose. Remember, these J matrices are just matrices with 1s in them. Okay, so I'll leave it to you to verify that that's indeed what it ought to be. Also, one more thing, and this will be important for us. Well, it might or might not be important for us, but occasionally it is important. This notion of positive semi-definiteness. A matrix M, we'll say, is positive semi-definite if for all vectors V of appropriate dimension, of course. You have that V, that's for all column vectors, by the way, all column vectors V. If I take V transpose, which is a row vector, multiplied by M, and then again by V, that this is greater than or equal to 0. Okay, one of your homework problems has to do with positive semi-definiteness, and so yeah, so it turns out that covariance matrices are symmetric and positive semi-definite. Finally, one more little application, and we'll go into this in depth, and we'll actually prove this in the next set of notes. But it turns out that we can see that in a very general way that we can actually write down our least squares coefficients in a very nice way when we're doing linear regression. It turns out it's if I have a data matrix, let me write this off to the side here. If I have a data matrix that looks like this, okay. First of all, I have a column of 1s, dot, dot, dot. And then the next column is a column of data. Okay. And if my y values, my response variable values are these guys, y1, y2, y3 to yn. And I can actually write down the expression for my least squares coefficient estimates as x transpose x, quantity inverse, times x transpose y. Okay? So y will be an n by 1. X transpose in this case will be a 2 by n. The transpose is a 2 by n. Okay, so you'll see that this is, when you multiply these two, you get a 2 by 1. X is, of course, a n by 2. X transpose is a 2 by n. So this is a 2 by 2. Its inverse, provided it actually exists, is a 2 by 2 as well. So I've got a 2 by 2 times a 2 by 1, which will give me a 2 by 1. Okay. So in the case of simple linear regression, this is just the column vector of beta naught hat and beta 1 hat. This will give you your intercept and your slope.